Hey guys, today we are looking at 3.2, which is going to talk about arc length and the sector of a circle. So we're going to start with arc length. We've got our formula for arc length over here. It's S. S is going to equal R times theta. R is the radius and theta is the angle. So an arc length is a measure of like part of the circumference of a circle. So just like part of around the circle. So we're talking about trying to find an arc length. We're trying to find just part of the edge of the circle. And so it's the radius times whatever that angle measure is. Something that's really important here, though, is that it does tell you that you need to make sure that the measure of the angle is in radians, which is why we're talking about it now after we just did 3.1, where we learned about radians. So let's look at some examples here. Example 1. A circle has a radius of 18.20 centimeters. Find the length of the arc intercepted by a central angle with a measure of 3 pi over 8 radians, and it says round to the nearest thousandth. So if I'm looking at my formula, S is equal to R times theta. I've got my R, my radius right here, and I've got my theta, my angle right here. So S is going to equal that 18.20 times my 3 pi over 8 for my angle measure. So I'm just going to multiply all that together in my calculator. I'm going to do my 18.20 times my 3 pi over 8. And when I plug all of that in, I get that S is equal to, rounding to the nearest thousandth, 21.441 centimeters. It is a measure around the circle, so we just use centimeters there. And there we go. There's our arc length. Okay, example 2. Same circle. It has the radius of 18.2 centimeters. Now we're finding the length of an arc intercepted by a central angle with 144 degrees as the measure. Now, this is where we got to be careful because it says the formula for r times theta for our arc length, the value of theta must be expressed in radians, not degrees. And you'll notice, excuse me, that right here, this is in degrees. So we need to convert this to radians. Convert to radians. So we just talked about how to do that in the last set of notes. I'm going to take that 144 degrees and I'm going to multiply it by pi over 180. So I get 144 pi over 180, which would simplify down to 4 pi over 144 over 180 simplifies down to 4/5. Then from there, I can plug it into my formula. My S equals R theta. My radius is still that 18.20, and now my theta is this 4 pi over 5. Okay, once again, rounding to the nearest thousandth, I can plug that into my calculator, 18.20 times my 4 pi over 5. So I get that S is equal to 45.742 centimeters this time. Okay, this should be a little bit of a review from geometry because you did do arc length in geometry. So let's kind of step it up a little bit and let's do some application problems. And let's kind of get a little bit more into the pre-cal level, into the college trig level of problems. So it says latitude gives the measure of a central angle with vertex at Earth's center, whose initial side goes through the equator and whose terminal side goes through the given location. So Reno, Nevada is approximately due north of Los Angeles. The latitude of Reno is 40 degrees north, and that of LA is 34 degrees north. The N in the degrees north means that it's north of the equator. The radius of the Earth is about 6,400 kilometers. Find the north-south distance between the two cities, round to the nearest thousandth. So we've got a nice picture here that helps us out. I'm going to zoom in on the picture. And it tells us that we've got Reno right here, a nice little city, and we've got LA here, nice little city. And we are trying to find the north-south distance between them. So we're trying to find this. Oop, let me pick a color that's going to show up better. This distance between these 2 points. Now, luckily, our picture is already labeled pretty nicely for us, and it's telling us that the distance in the angle is 6 degrees, which is the 40 degrees minus the 34 degrees. That makes sense. 40 minus 34 gives me 6 degrees. But remember, if we're talking about arc length, we need to be dealing in radians, not degrees. So before I can plug it into my S equals R theta, I need to convert to radians. So I'm going to take that 6 degrees and I'm going to multiply it by pi over 180. So I get 6 pi over 180, which is going to simplify down to pi over 30. Okay, it does tell us that the radius of the Earth is about 6,400 kilometers, so I can plug that into my formula. So 6,400 times now my angle in radians, the pi over 30. It says round to the nearest thousandth, so I'm going to go ahead and plug it into my calculator. Get that decimal answer. Make sure you're paying attention to what it tells you to round to. Sometimes it'll give you round to the nearest thousandth. Sometimes it'll give you round to the nearest hundredth, or round to the nearest whole number, or round to the nearest hundredth, maybe even, or hundred, not hundredth. Or sometimes leave it in pi, leave it in terms of pi. Okay, so when I do this and plug it into my calculator, I get that that arc length is equal to 670.206 kilometers. km is kilometers. So those two cities are 670.206 kilometers away from each other. Let's look at another one. The figure shows one end of a game court with a 3-point line colored red. What is the total length of the 3-point line to the nearest foot? So zoom in on the picture again. It tells us right here that this part is 13 feet, which means over here, this part is also going to be 13 feet. So I know I can do 13 plus 13 over here, but I need to figure out what that middle curve section is, which is going to be our arc length. So I need to figure out what that middle length is. 13 plus something plus 13. So that's where I'm going to use my S equals R theta. Now if I look here, they've given me my R. It's 24.75 feet. So I can say 24.75 times some angle. The problem is that the angle they gave me is in degrees. So if I have 139.77 degrees, I need to convert to radians. So I'm going to have 139.77 times pi over 180. Okay, that would give me 139.77 pi over 180. And since we're going to have to plug that all into our calculator because it wants us to round to the nearest foot, I can just leave that fraction like that. I know we don't really want decimals in our fractions, but if it's going to go into the calculator anyways, it doesn't really matter a whole lot here. So I'm going to plug that in, move my parentheses over so I've got a little more room. So 139.77 pi over 180. And this is what I can plug into my calculator right here. It does say to round it to the nearest foot. So when I plug this into my calculator, the 24.75 times that 139.77 times pi over 180. My calculator spits out about 60.376-ish, which to the nearest foot would be 60. So that's going to be the missing gap that was right here. So I'm looking at 13 plus 60 plus 13, which is going to give me 86 feet. So to the nearest foot, the total length of the 3-point line is 86 feet. Now, so far, we've just done the arc length, which is like the little bit of the circumference around the circle. The other formula that we're going to look at today is the sector of the circle, which is like the area of a portion of the circle. So it's like taking a pie piece and trying to find the area of a pie piece of the circle or a piece of pizza or something like that. So our area of a sector formula that we're going to look at is this one right here, 1/2 r squared theta. The sector of a circle is the portion of the interior of the circle intercepted by a central angle. So it's the whole shaded area that we have right here, the whole piece of the pie, the whole pizza piece, the whole section there. And so it's an area instead of just like the circumference going around the circle. And once again, our theta does need to be in radians, which is why we're learning about it today, after we learned about radians last set of notes. So let's look at a couple of examples. We're just going to kind of go ahead and skip to the application problems and use our formula there. And we do have the caution right here that says what I was just saying. As in the formula for arc length, the value of theta must be in radian when this formula is used for the area of a sector. So it says a center pivot irrigation system provides water to a sector-shaped field with the measures shown in the figure. Find the area of the field, round to the nearest thousandth as needed. The center pivot irrigation system is a sprinkler that you guys are used to seeing. You know, the sprinkler that kind of goes like off in an arc and then goes all the way back and then goes back and forth in the little arc. That's what's happening here. So it's going like back and forth over this little section and then goes back. So that's what we're looking at here. We need to find the total area of that triangular kind of cone curved little sector of a circle that it covers. And you can say it's a sector because you can see how this is curved down here and not just a straight across. So it's not just a triangle, it's an area of a sector. So our formula is 1/2 r squared theta. They gave us our radius, our r, 321 meters. So I'm going to have 1/2 times 321 squared. And they gave us our theta, but our theta is in 15 degrees. So we need to, once again, convert to radians. If I have 15, I'm going to multiply it by that pi over 180. So I get 15 pi over 180. And that 15 over that 180 is going to simplify to pi over 12. 1/12, so pi over 12. So that's what I'm going to plug in for my theta, the pi over 12. So my area is going to be that whole thing. In the calculator, rounded to the nearest thousandth as needed. So 1/2 times my 321 squared times, oh, I forgot the 1 there, pi over 12. When I plug that in, I get 13,488.035 meters squared because it is an area. And there we go. And our last question for this set of notes. Ashley has a pizza that she wants to share with her 5 friends. If the pizza is 15 inches in diameter and each person will get one slice, what is the area of each slice? Round to the nearest hundredth as needed. So, first thing, Ashley is sharing it with her 5 friends. So, if we're talking about how many people there are total, if it's Ashley and her 5 friends, that means there's 6 people total. So, what we need to figure out is if we have a full 360 degrees or a full 2 pi all the way around the circle, we need to divide that between 6 people. So 2 pi over 6 or pi over 3. We're taking the entire way around the circle and cutting it into 6 for the 6 people. So, full circle divided by people. That's how we get to our angle of pi over 3. The other thing we have to look at too is it says that it's 15 inches in diameter. But for our formula, we don't need the diameter, we need the radius. Remember, our formula is 1/2 r squared theta. So I just found the theta. It's the pi over 3, but my r is not going to be 15, but it's going to be half of that. Remember, the radius is half of our diameter. So 15 over 2 squared. So make sure that you're really, really paying attention to all the information that they give you in the problem so you know how to break down all the information to put into your formula. You can't just plug in 15 because you don't need the diameter, you need the radius. And if we're talking about 6 people total, well, how do I find my angle? I take the full way around the circle, 360 degrees, or 2 pi, since we need it in radians, and divide it by the 6 people that I have. From here, I've got my formula. I need to round to the nearest hundredth, so I'm going to plug all this into my calculator. I'm going to do my 1/2 times that 15 halves squared times my pi over 3. And that spits out my answer of 29 point, rounding to the nearest hundredth, so 4.5 inches squared. That's the area of each slice. And there you go. That's it for this set of notes. Let me know if you have any questions. Make sure to get started on your assignment that goes with this. And y'all have a good day.